Okay, let's unpack this. Today, we're doing a deep dive into some uh, really fascinating engineering.
Absolutely.
We've got this audio excerpt describing a portable 1.25 kiloj coil gun. Sounds intense.
It is. And our mission really is to cut through the technical stuff.
Yeah, to understand how they actually made this work, right?
Yeah.
How do you make something so powerful, well, portable?
Exactly. We'll break down how it's built, how it operates, and maybe highlight some of the really clever bits of engineering involved. It's about managing power, precision, and making it handheld.
So power, that's the first hurdle, isn't it?
Yeah.
How do you power something like this compactly? The source mentions a 12-volt high-drain battery.
Yeah, think of it as the core power source.
Oh, wow.
It's apparently modified slightly to fit inside the main body, the receiver.
Okay, and it goes through a fuse for safety, I guess.
Right, standard safety measure. Then the power goes out through a 9-pin connector.
And that connector links to the foregrip.
Precisely. And that foregrip, well, it's doing a lot more than just being a grip. It's kind of the control hub.
Control hub. Okay, what's inside?
Well, inside there, you've got a voltage regulator board. This thing is crucial.
Why is that?
Well, it takes that 12 volts coming in and steps it down, very precisely, to two different voltages, 3 volts and 5 volts.
Okay, 3 and 5 volts. What are they for?
The 5 volts, that powers a little digital voltage meter so you can actually see the capacitor charge level.
Ah, useful. And the 3 volts.
That handles a couple of things. It powers the aiming laser, and really importantly, it provides the gates signal to the SCR when it's time to fire. We'll get back to that SCR.
Got it. Wow, that's quite a bit going on just for power management and something you hold. So, okay, you've got power sorted. How do you actually charge it up? Get it ready.
Right, the charging cycle. You flip a switch, usually located over the handle based on the description,
Okay.
and that sends power to the charging circuit, which is also housed in that foregrip.
The busy foregrip again. What's in the charging circuit?
The key component here is something called a ZVS flyback driver.
ZVS flyback driver.
Yeah.
Sounds complex.
It's very efficient at generating high voltage from a low voltage input. It works with a flyback transformer to really ramp up that voltage.
So it's basically a voltage booster circuit designed to be efficient and compact.
Exactly. Perfect for this kind of application where you need to charge capacitors quickly without huge, heavy components.
Okay, so you've boosted the voltage. What happens next?
That high voltage, which is AC at this point, goes through a bridge rectifier.
Ah, okay. That converts it to DC. Right. Capacitors need DC.
Precisely. Smooth DC current is what you need to charge up those main energy storage capacitors.
And how does it know when to stop charging? You don't want to overcharge those things.
Good point. There's a comparator circuit built in. Think of it like a smart sensor or a watchdog.
Okay.
It constantly monitors the voltage across the capacitors. When it hits a specific preset level, the comparator tells the charging circuit, okay, stop.
And you can set that level.
Apparently, yes. The description mentions a knob to adjust that final charge voltage, so you have control over the energy level.
All right. So the caps are charged, the voltage meter shows it's ready, laser's on, you're locked and loaded. How do you fire it? How do you release all that stored energy?
This is the critical part. The trigger mechanism is described as a rocking switch.
A rocking switch.
Yeah. When you pull or activate that trigger, it does two things almost instantly. First, it cuts power from the charging circuit,
And it
safety measure.
makes sense. Don't want it charging while firing.
Right. And second, it sends that little 3-volt signal we mentioned earlier straight to the SCR's gate.
The SCR, the silicon-controlled rectifier. Our source called it a large semiconductor.
That's it. You can think of the SCR as a very heavy-duty, very fast electronic switch. It's designed to handle huge currents.
So that tiny 3-volt signal is like the key.
Exactly. That 3V hits the gate, and it tells the SCR to open the floodgates, basically. It switches on instantly. And then all the energy stored up in those capacitors, that 1.25 kilojoules, gets dumped just instantly into the main coil.
Wow. A massive sudden burst of current through the coil.
A huge burst. And that creates an incredibly intense magnetic field inside the coil, just for a fraction of a second.
And that magnetic field is what grabs the projectile and launches it down the barrel.
That's the principle of a coil gun, yeah. A purely electromagnetic launch.
The source mentioned one recurring observation throughout all this. Heat. Seems like that was a big factor.
Absolutely. Generating that much power, transferring it that quickly, heat is almost inevitable. The original builders noted it as a significant byproduct. It tells you just how much energy is being moved around and converted.
Yeah, managing heat in compact power electronics is always a challenge.
Definitely. But despite that, they clearly felt they'd achieved something remarkable. The source uses phrases like, "this was a triumph" and "huge success."
It's hard to overstate my satisfaction. You can really feel the accomplishment there.
Yeah, building something like this from scratch, making it work reliably and be portable, that's a serious engineering feat.
So what does this all mean for you listening?
Well, when you break it down like this, you start to see how these different systems, the power supply, the voltage regulation, the high voltage charging, the fast switching, all have to work together perfectly. It gives you, I think, a much deeper appreciation for the layers of design behind something that, from the outside, might just seem like pulling a trigger.
Absolutely. What's fascinating here is seeing that intricate dance of components. You've got the battery providing raw power, regulators refining it, the ZVS driver boosting it, capacitors storing it, and the SCR unleashing it, all coordinated in a handheld device.
It really makes you think, doesn't it?
It does. And maybe a final thought to leave you with. As we see technology pushing for more power in smaller and smaller packages, whether it's batteries, electronics, or devices like this Coilgun,
Yeah.
how will engineers continue to solve these fundamental challenges, especially managing things like the waste heat, the stresses, ensuring safety and reliability? It's a constant balancing act. And seeing examples like this really highlights the ingenuity involved.